Okay. So what we discussed in the last class, we have gone through the quantization noise power evaluation for a uniform quantized PCM system. Okay. And so coming to the slides, what we covered in the last class, first let us move through that. So initially we have defined the input for the quantizer as continuous amplitude sample, that is x of NTS, and output be xq of NTS, which is a discrete amplitude sample. And then we have defined the quantization error or the error inherited due to the process of quantization as the output of quantizer, which is xq of NTS minus x of NTS. Okay. So we have defined what is quantization error. It's the difference between the quantized signal and the sample signal, that is xq of NTS minus x of NTS. So remember this point and take that equation as 1. Okay. And from the characteristics of characteristics shown here, that is the transfer characteristics of quantizer, you can calculate we can evaluate the quantization error for the positive staircase waveform as plus delta by 2, and for the negative staircase waveform you can evaluate it as minus delta by 2. So total quantization error range from minus delta by 2 to plus delta by 2. Okay, so that we mentioned in the equation 4. And next we have defined the step size. So how we have defined the step size? It is the total ratio of total continuous amplitude range divided by the number of representation levels. Okay, so total continuous amplitude range is from x min to x max. Here x min is minus x max and maximum extremity is plus x max. Okay, so total continuous amplitude range will be the difference between the maximum extremity to that of the minimum extremity. So x max minus x minimum divided by L. Okay, so because x min is the minus x max, just we replace it the value. So x max minus of minus x max, you will get it as 2x maximum divided by L. But what is L? L is the number of discrete amplitude levels or representation levels. You can equate that to 2 power n. You can equate that to 2 power n, where n is the number of bits per sample. Okay. If the signal x of t is normalized, the x max will be equal to 1. So therefore, you can replace x maximum as 1 for normalized input. So you can get delta as 2 by L. So you can directly equate that as 2 by 2 power n, because L equals to 2 power n. So here from this slide you should remember 2 points. One is quantization error, which is xq of NTS minus x of NTS, because that is the error inherited due to the process of quantization. And second thing is the same in the first point you should remember one more thing, that error range from minus delta by 2 to plus delta by 2. Okay, and the second point that you should remember is that the step size is equal to, general expression for step size is 2x maximum divided by 2 power n. Okay, so for normalized input, x maximum is equal to 1. X maximum equals to 1. So it is equals to 2 by 2 power n. Okay, so remember these 2 points. One is the error, second one is the definition for step size and the general expression for it. Okay, remember these 2 points from this slide. And next what we did, we have calculated the probability distribution function for the quantization error. Okay, we are going to calculate the quantization error. We are going to calculate the quantization error PDF, probability distribution function. And here we know that the error varies from minus delta by 2 to plus delta by 2, that we studied in the last slide. Okay, so because it is uniformly distributed from minus delta by 2 to delta by 2 with a magnitude of delta by 2, okay, So here while representing the probability distribution function, x-axis is the error. Okay, and y-axis is its distribution. Y-axis is its distribution and x-axis is the error. Okay, what is error? Error is the thing inherited by the quantization, by the process of quantization. It is a noise inherited by the process of quantization. So it ranges from minus delta by 2 to plus delta by 2. Okay, so that's why you can observe from the uniform quantization, that whenever signal range from A to B, whenever the signal range from A to B, okay, then its a distribution function will possess a magnitude of 1 by B minus A, 1 by B minus A. So therefore, whenever the quantization error range from minus delta by 2 to plus delta by 2, its distribution will have a magnitude of 1 by B minus A. Here B will be delta by 2 and A is minus delta by 2. So finally you can get 1 by B minus A as 2 by 2 delta. So overall magnitude will be 1 by delta. Okay, so that's what we represented in the bottom equation. So here we have represented one equation, that is general expression is fx of x, but here we are going to evaluate the distribution function for error. So that's why we represent it as f suffix e of e. And what is its magnitude? Its magnitude is 1 by delta whenever error lies in between minus delta by 2 to plus delta by 2. And beyond that range, the error is the distribution, we don't have error distribution. So error is distributed only from minus delta by 2 to plus delta by 2 with a magnitude equal to 1 by delta. Please remember this equation. So 3 equations you should remember. First is step size delta, which is 2x max by L, or 2x max by L is 2 power n. Okay, 2x max by 2 power n. And second point is error range from minus delta by 2 to plus delta by 2. So its probability distribution function is magnitude is 1 by delta within that range. So 2 points. Okay, next let us move to the next slide to calculate the signal to noise ratio. So prior calculating the SNR for quantizer, let us define it. Okay, so it is in general you can define it as the ratio of normalized signal power to normalized noise power. Okay, so first let us focus on the denominator section. So that is normalized noise power. Let us assume the signal power as some capital P. For some time, let us assume it as capital P. And first of all, let us evaluate the normalized noise power. Okay, so here noise is the quantization error. Okay, so how can you define the noise power? It is defined as the ratio of mean square value of the noise signal to that of load resistance. Okay, it is defined as a ratio of mean square value of the noise signal to that of load resistance. For normalized input, in general, the load resistance value R equals to 1 ohm. R equals to 1 ohm. So what is the quantization noise power here? Expectation of error square, nothing but mean square value of noise signal divided by 1 ohm. So I can say that the quantization noise power is directly equal to mean square value of the function. Okay, mean square value of the error under normalized load resistance. So first of all, let us calculate the expectation of error square to define the quantization noise power. So once we get this n value, quantization noise power, let us take it as capital N. Then we can directly substitute it in SNR. Okay, so now let us calculate the mean square value of the error. See, always remember here, quantization noise is nothing but the quantization error, the noise inherited by the process of quantization. Okay, so let us calculate the mean square value of the noise signal first, that is expectation of error square. So from the generalized expression, expectation of x square for a function x of t is generally equal to minus infinite to plus infinite x square fx of x dx, where fx of x is the probability distribution function of the signal x of t, of the signal x of t. Okay, now let us replace the same thing in terms of error. So expectation of error square will be integral minus infinite to plus infinite error square into fe of e dE. But what is fe of e? Already in the last slide we have defined the probability distribution function as one of the error as 1 by delta, as 1 by delta within the range minus delta by 2 to plus delta by 2. Okay, so that's why change the integration limits to minus delta by 2 to plus delta by 2 and fe of e as 1 by delta. Okay, so in the next slide, please let us change the integration limits to minus delta by 2 to plus delta by 2 and replace the generalized PDF expression for error as 1 by delta from minus delta by 2 to plus delta by 2. So integration limits will change and the function value will also change, that is 1 by delta. Okay, so this is about the expectation of error square, that is mean square value of the quantization error. Now we replaced fe of e as 1 by delta, and this 1 by delta is the magnitude which is independent of the integration. So take that 1 by delta outside the integral and get the integration of error e square dE. Mean that what is the integration of x square dx? It is equals to x cube by 3. So using that expression, let us move to the next slide. So expectation of error square is 1 by delta because it is outside, it is a factor independent of the integration. So let us take it outside. So it will be 1 by delta into e cube by 3, where the error range from minus delta by 2 to plus delta by 2, minus delta by 2 to plus delta by 2. Please substitute the limits from minus delta by 2 to plus delta by 2, and therefore you will get delta by 2 whole cube by 3. So minus of, here we have delta cube minus delta whole cube, so you will get minus here. So minus of minus leads to a summation. So that's why here you will get delta cube by 8 plus delta cube by 8. So it will be 2 delta cube by 8 inside the integral divided by 3 delta. So delta, one of the delta from the numerator gets cancelled, and here we have 4 because 2 by 8, it will be 1 by 4 into 1 by 3. So it will be delta square by 12. See, please all of the students remember this equation. What is the mean square value of the quantization error? It is delta square by 12. Okay, mean square value of the quantization error you obtained as delta square by 12 because we assumed the error range from minus delta by 2 to plus delta by 2. Please recollect the equation. What is delta? Delta is 2x maximum divided by L. 2x max divided by L. Okay, and you can replace that delta, while calculating the SNR. And before that, please let us define what is normalized noise power. So denominator of SNR is the quantization noise power. It is defined as the mean square value of the quantization error to that of the load resistance. So let us represent the quantization noise power as capital N. Let us represent the quantization noise power as capital N, which is expectation of E square divided by R. For example, assume the value of resistance R as 1 ohm. Take the resistance R as 1 ohm so that you can calculate N as directly equal to the expectation of error square. Okay, but what is mean square value of error? Already we got it as delta square by 12. This is very, very important regarding your examination. Derive the expression for quantization noise power as delta square by 12. This is the denominator part of SNR. Okay, and here because we are assuming the normalized resistance value, you can take it as 1 ohm. That's why the quantization noise power is directly equal to the expectation of error square. Okay, so please replace the value of delta in the above expression, what is delta? Already we defined, it is the difference between the maximum extremity magnitude to minimum extremity magnitude of the continuous range divided by the number of discrete amplitude levels, that is capital L. But this number of amplitude levels can be defined as 2 power n, where n is the number of bits per sample. And already we defined it as both the extremities have same magnitude of x max. So that's why x max minus of minus x max. So negative extremity will be minus x max. So total you will get 2x maximum divided by L, or 2x max by 2 power n. So from the equation 2 we have concluded it as 2x max by 2 power n. Okay, and now please substitute the value of delta as 2x max by 2 power n in the general equation of quantization noise power. So n will be 2x max by 2 power n whole square divided by 12. So till now we are calculating the denominator part of SNR, that is quantization noise power, capital N, which is equals to delta square by 12, where delta is the step size, or you can also call it as quantum. It is equals to 2x max by L, or 2x maximum divided by 2 power n. Okay, whole square divided by 12. Let us simplify this in the next slide. Let us move to the next slide. So in the next slide, what we did, so we got n, that is the quantized noise power, that is the denominator of SNR we got. It has delta square by 12. But what about the numerator? For some time, please assume that as signal power as capital P. Based on the input signal, so based on the input signal x of t or m of t, you can calculate the value of P and you can substitute in this general expression. So prior that, let us evaluate the general expression for SNR, assuming or under the assumption that the normalized signal power is capital P. Let us assume the normalized signal power as capital P, and already we evaluated the denominator part as quantization noise power. How much we got? Delta square by 12. Okay, so SNR equals to P by N. So where P is the signal power, and N is delta. Okay, x max divided by n. Okay, so and what is n? N is delta square by 12. N is delta square by 12, where delta is 2x max divided by 12. 2x max divided by 12. Please substitute here. Please substitute the value of delta in this expression, and you can obtain it as, student number, 2 square x square max divided by 2 power 2n. You will get here, because 2 power n whole square is 2 power 2n. So that is down to the denominator. So you can take this 2 power 2n to the numerator, because down to the denominator you will have 2 power 2n and 12. So take 12 2 power 2n to the numerator, and 2 square you will have in the denominator. So 4 and 12, if you cancel, you will get 3 in the numerator. So 3p 2 power 2n divided by x square max. Simply this 2 power 2n you can define it as L square, because 2 power n is L. 2 power n is L. So 2 power 2n will be L square, where L is the number of representation levels or amplitude levels of the quantizer. Okay, so what is the general expression for SNR with the normalized signal power as capital P? SNR equals to 3pL square by x square max. Please remember this equation. This is very, very important. What is the general expression for quantization noise power? Delta square by 12, where delta is 2x max by 2 power n. And what is the general expression for SNR? SNR is the ratio of normalized signal power to normalized noise power. And let us assume the normalized signal power as capital P, and denominator already we calculated as delta square by 12. Please replace the value of step size as 2x max by L, where L is 2 power n. So upon simplification, you can get it as 3p into 2 power 2n divided by x square max. Okay, so that is equals to 3pl square divided by x square max. Okay, so this is the equation that you should remember throughout this subject. Okay, so throughout the time you should remember the SNR of a PCM system under uniform quantization as 3pl square by x square max, where p is the normalized signal power and L is the number of discrete amplitude levels, which you can write it as 2 power n. Okay, now if the signal x of t is normalized, okay, above one is a general expression. If, for example, if you consider the input signal x of t as normalized signal, then x of t, if you are normalized, then the maximum extremities will be 1, the maximum magnitude will be 1. So that's why x max you can replace it as 1. So if you replace x maximum as 1 in the denominator, so SNR expression will be 3pl square, 3pl square, because divided by 1 square, it will be 1 only. So directly you will get 3pl square as the general expression for SNR under normalized input. And one more point that you should remember is that always the signal power capital P, normalized signal power capital P, the value is always less than or equal to 1 if the signal x of t is normalized. Otherwise it is very higher quantity. If the signal x of t is normalized, then the destination signal power capital P is always less than or equal to 1. So what happens to our SNR then? SNR for normalized x of t is 3pl square, because x max is 1. But what is the magnitude of p? It is always less than or equal to 1 for normalized x of t. So therefore we can conclude that if the signal x of t is normalized, then p will be less than or equal to 1. So what happens to our SNR? It is less than or equal to 3l square. It is less than or equal to 3l square. Okay. So this is the point that you should remember. So what is the general expression for SNR? 3pl square by x square max. Okay. For normalized input, x max is equal to 1 and p is less than or equal to 1. So that's why SNR will be less than or equal to 3l square. Okay. Once again assume the value of p and let us evaluate the SNR in decibels. This is the SNR value which is less than or equal to 3l square for normalized input x of t and p less than or equal to 1. Okay, please all of you, let us calculate the SNR in decibels. Let us evaluate the SNR in decibels. Okay, let us move to the next slide. So from the next slide, you can observe SNR as less than or equal to 3 into 2 power 2n. This is nothing but 3 into L square, where L is 2 power n, where L is 2 power n. Okay, so L square will be 2 power 2n. So it is less than or equal to 3 into 2 power 2n, where P is less than or equal to 1. Now please observe SNR in decibels. What is the general expression for SNR in dB? 10 log the SNR general value. But what is the general value of SNR for normalized signal power? It is less than or equal to 3 into 2 power n. So it is less than or equal to 10 into log 10, 3 into 2 power 2n, 3 into 2 power 2n. Okay, so it is in the form of log x into y, log x into y. You can split this as log x plus log y, log x plus log y. So 10 log 3 plus 10 log 2 power 2n, 10 log 2 power 2n. So log 3 value is generally 0.477. So multiplied by 10 you will get it as 4.77. And here you have log x power y. Here you have log x power y. So it will be, so if you observe here, it is log x power y. So you can represent it as y log x, y log x ante 2n log 2 base 10. Okay, so 2n multiplied by 10, it will be 20n log 2 base 10. So the value of 20 log 2 is 6.02. 20 log 2 is 6.02 multiplied by n. What is n? N is the number of bits per sample or per frame, how many number of samples are there. So that is 6.02 into n. So this is the general expression for SNR in dB for normalized input and normalized signal power. For normalized input x of t, x max equals to 1 and p is less than or equal to 1. So under that assumption, we calculated the SNR in dB as less than or equal to 4.77 plus 6.02 n plus 6.02 n dB. Okay, so what is the, so you can approximate that to 4.8 plus 6 in dB. See, this approximation you can do in the examination only when they ask you to calculate the SNR in dB, for the expression derivation. For the SNR expression, you can approximate, but while doing problems, don't take the approximated expression. Okay, so take it as 4.77 plus 6.02 n decibels. So what are the expressions that you should remember for during this module? First thing is error. Okay, error ela untundi, it range from minus delta by 2 to plus delta by 2. And what is the second point that you should remember? Delta. Delta is a step size which is 2x max by L, where L is 2 power n, ante 2x max by 2 power n. And what is the third point that you should remember? The probability distribution function of error. How much? 1 by delta, because 1 by b minus a will be the magnitude. So 1 by delta whenever error lies in between minus delta by 2 to plus delta by 2. Okay, so upon substituting the mean square value of the noise signal, divided by resistance as 1 ohm, then you can get the quantization noise power, capital N. So we substituted the value of quantization noise power, capital N, as delta square by 12. How you got this? This is nothing but the mean ratio of mean square value of the error to that of resistance. Okay, to that of resistance. So mean square value of the error signal, expectation of error square, is equals to minus infinite to plus infinite error square into Fe of E dA. Fe of E, we replaced it as 1 by delta and we changed the limits as minus delta by 2 to plus delta by 2. So upon simplification, we got the quantization noise power, capital N, as delta square by 12, where delta is 2x maximum divided by L. Okay, or 2x max divided by N. Okay, we simplified that and we took the value of or we assumed the value of normalized signal power as capital P. We assumed the normalized signal power as capital P and noise power N as delta square by 12. Okay, then we got general expression for SNR as 3p L square by x square max. So what is the general expression for SNR? 3p L square divided by x square max. Okay, next what we did? For normalized x of t, x max is 1 and p value is less than or equal to 1. Okay, so then under these assumptions, we got SNR value less than or equal to 3 into 2 power 2n. So if you want the signal in decibels, so 10 log the respective value in normal values. So that is 3 into 2 power 2n. So upon simplification, so because log xy you have split it into summation. So finally you got less than or equal to 4.77 plus 6.02 n. So that is the general expression. under normalized input and normalized signal power. Okay, let us move to the next slide. Here we have given one example, and before going to this example, one of the student please respond and tell me what is the general expression for quantization noise power. So only two expressions you should remember. One is quantization noise power and another one is SNR for the PCM. Okay. So what is the expression for quantization noise power? How much you got? Capital N. One of the student please respond and tell me.
Delta square by 12.
Delta square by 12. What is delta? Amma, what is delta? 2x max by
2x max by 2 power n.
By 2 power n. Yes, very good. 2x max by 2 power n. So that is normalized. So based on that, you can get the quantization noise power capital N as delta square by 12. Very good. Next, other student, any one of you, please respond and tell me what is the general expression for SNR. I am asking not in decibels. Tell me the general expression for SNR under the assumption of signal power as capital P.
3PL square by x square max.
Yes, 3PL square by x square max. Very good. Thank you. 3PL square by x square max. Now, under the assumption that normalized input and P less than or equal to 1, what can be the value of SNR? It will be less than or equal to 3L square. Okay. So, in decibels, how much you got? In decibels, we got it as 4. So, how much you got? It is 4.77 plus 6.02 N. That is in decibels. Okay. Now, any other student, please read this question. What is this question? Here, there is no need to consider the signal power as capital P, because the signal is given as x of t, which is m of t, which is am cos 2 pi fmt. Signal is given to you here. Okay. So one of the student please respond and read this question. Is this slide visible to everyone? So please go through that question, and one of the student please read this question. Here there is no need to consider the signal power as capital P. Okay, because signal is given to you x of t. So one of the student voluntarily please come and read. See, any one of the student please read that question given there.
Derive the expression for the SNR
Of uniform
quantized PCM
system.
When the input signal x of t is equal to
M of t. Okay, that is message signal, which is given as am cos 2 pi fmt.
Also prove that when the maximum amplitude of the message signal AM is equal to 1 volt.
1 volt. SNR in dB is how much? You should get it as 1.76 plus 6.02 in dB. Now, what is the magnitude of M of t here? Ma, what is the maximum amplitude of x of t?
AM cos 2 pi.
Amplitude is only AM. Angle will be inside the cosine term. Okay. So, amplitude ante enta AM. Okay. So, maximum amplitude of message signal is A suffix M. Now, so what you are going to calculate? You should calculate the SNR. So, in order to calculate the SNR, first you should calculate the peak power or signal power. Okay. So, how can you calculate the signal power? We assume it as capital P. So, take the same variable capital P and you are given with the signal. So, what is the definition for signal power? It is defined as the ratio of mean square value of the input signal to that of resistance. For the normalized resistance, you can consider it as 1 ohm. But what is a mean square magnitude? Mean square magnitude is nothing but the maximum value by root 2. So what is the maximum amplitude of message signal? AM. AM by root 2 will be the RMS value, mean square value. So whole square, because we need VRMS square divided by R. So VRMS is nothing but the maximum amplitude of message signal divided by root 2 whole square divided by R. So it will be AM square by 2R. If the value of resistance is given to you, then you can consider it as AM square by 2R. If the resistance value is not given, or if the signal, input signal is normalized, then you should consider R value as 1 ohm. Then remember this signal power expression, because whenever a signal is given to you, then you should get the peak power or signal power, normalized signal power capital P as AM square by 2R. R is generally 1 ohm if not given in the problem. If it is given, you can directly substitute the value as AM square by 2R. Okay, so what is the expression for peak power? That's why represented in red color. So P is equals to AM square by 2R in general. If it is normalized, R is 1 ohm. And even sometimes in the problem, if it is not given to you, take R as 1 ohm and solve for the signal power as directly AM square by 2. For example, if the maximum amplitude of message signal is given as 2, then AM square by 2, ante 2 square by 2. So peak power is 2 watts. Okay. So like that, so similarly, what is the normalized maximum input? X max is equal to 1 volt. So SNR ఎంత అవుతుందమ్మా? What is the general expression for SNR? We know that SNR general expression is 3p L square by X square max, where P is the signal power. How much signal power here for this AM cos 2 pi m FMT? AM square by 2. So please replace P as AM square by 2. AM square by 2 and X max as 1, because the signal, input signal X of t is normalized. Okay, so take X max as 1 volt and please replace P as AM square by 2. If you replace like that, you can observe the SNR expression as 3 into AM square into L square divided by 2. So under the assumption that X max is equal to 1 volt. So finally you got some expression 3 into AM square into L square divided by 2. That is the first bit. So we got the expression for SNR for the input signal X of t, which is AM cos 2 pi FMT as 3 by 2 AM square L square, 3 by 2 AM square L square. Okay, what is the second bit? Also prove that when the maximum amplitude of message signal AM is equal to 1 volt, evaluate the SNR. So what is the SNR expression for the signal X of t, which is AM cos 2 pi FMT? 3 AM square L square by 2. But what is AM? AM is 1 volt. So 3 by 2 L square, because AM is 1 volt. So SNR expression becomes 3 by 2 L square. Now how can you get the SNR in decibels? Actually you should calculate the SNR in decibels. So SNR in dB will be 10 log 3 by 2 L square. But what is the relation between L and N? See, at any cost, ultimately you should be able to derive the expression and represent the SNR in decibels in the form of number of bits per sample only. Okay, in the form of N, not in the form of L. Okay, you should be able to represent the SNR in decibels in the form of number of bits per sample. Ante N form loki techesukovali, not in L form. But what is the relation between number of amplitude levels and number of bits per sample? We know that L is equals to 2 power n. So 3 by 2 L square. Please replace L as 2 power n. So L square will be 2 power 2n. L square will be 2 power 2n. So split it. So it is in the form of 3 by 2 2 power 2n inside the bracket. So 10 log 3 by 2 plus 10 log 2 power 2n decibels. Okay. So log 1.5 value is 0.176. Multiplied by 10, you will get it as 1.76. Okay. And log x power y, it is in the form of log x power y. So it will be y log x, y log x. అంటే మనకి ఎంత వస్తుంది 20n log 2 వస్తుంది. Okay, 20 log 2 value is 6.02 multiplied by n. So finally you got the SNR in decibels as 1.8 plus 6.02 n decibels. Okay, so what we did here, we in this above problem we assumed x of t as am cos 2 pi fmt, and so finally peak power p can be am square by 2r. This is the general expression where because x of t is normalized, r will be 1 ohm and x max will be 1 volt. Okay. And please assume maximum magnitude of x max as 1 volt. So upon doing like this, you can get SNR as 3 am square L square by 2 as the general expression for the signal am cos 2 pi fmt. Okay. And but what is the one more thing here? Am is given as 1 volt. So substitute am as 1 volt and get the SNR in decibels. So apply the SNR dB expression. So 10 log the respective value of SNR. And upon evaluation you got it as 1.76 plus 6.02 n decibels. Okay, this type of problems you need to solve in the examinations. Okay, and this is one more problem given to you. This is one more problem. Please read this problem. So I will call one of you. L9 is there? Ma L9. L9. L8. L8. Okay, L9. Ma. Okay, ma L9. Can you read this question first? Please read this question.
Derive the expression for the SNR of the uniform quantized PCM system when the input signal x of t is equal to m of t is equal to 2 cos 2 pi into 250t.
Okay.
Also calculate the SNR in dB for L is equal to 128 and L is equal to 256 PCM system.
Okay, okay. Now you observe this equation and tell me what is the maximum amplitude of message signal AM entama L9. What is the maximum amplitude of message signal here? AM enta 2 volts. What is the maximum frequency of message signal FM?
250.
Yes, 250 hertz. Okay, okay, very good. So what is the general expression of SNR? Can you please tell me the general expression of SNR for a PCM system?
3p into L square.
3p L square, 3p L square by x square max. X max you can consider it as 1. And p power is am square by 2. Okay. So what is the peak power? Peak power p is equals to am square by 2, because in the last slide itself we solved, because am by root 2 whole square divided by r. So am square by 2r vastundi and r is 1 ohm. So it will be am square by 2. So anyhow SNR general expression for this type of input signals x of t is 3 am square L square by 2. And what is am here from the given question? Am is 2 volts. So 3 into 2 square into L square divided by 2. Okay. So finally you got it as 6L square. So because 2 square in the numerator and you have 2 in the denominator. So finally it is in the form of 3 into 2 square divided by 2. So it will be 6L square. But what is the relation between L and N? L is the number of amplitude levels, which is equals to 2 power N, where N is the number of bits per sample. So finally you should deduce the expression in the form of N only. So 6 into 2 power 2N. Okay, you got SNR like that. But what is the second bit actually here? You should be able to calculate the SNR in decibels for some value of L, that is L128 and L256. So that's why you should represent the SNR in decibels first. So you got SNR as 6 into 2 power 2N. Okay, please represent that in decibels. Decibels ela represent chestaru 10 log of 6 into 2 power 2N. Once again split that log xy into log x plus log y. So you will get 10 log 6 plus 10 log 2 power 2N. The second part ఉంది కదమ్మా ఏంటి 10 log 2 power 2N. You can represent 10 log 2 power 2N as 20N log 2. 20N log 2. Okay, that 20 log 2 is nothing but 6.02. So that 6.02N plus 10 log 6 value is 7.73. Okay, so that's why you got SNR in decibels as 7.73 or 7.78 plus 6.02 N. Okay, now is this problem over? No, you have to calculate the SNR in dB for L128 and L256 PCM. Now one of the student please respond to me whenever the value of L equals to 128, ante whenever you have 128 number of amplitude levels, then how many bits per sample are there? Once again I am asking you. So if we have 128 number of amplitude levels are there, the L is given to you, then how many number of bits per sample are present for L128 PCM system? Because L, any one of you.
7 bits, ma'am.
Why? Because L equals to 2 power N. L equals to 2 power N.
2
So
power
you
N.
can yes, very good. For 128 PCM system, you can represent it in the form of 2 power as 2 power 7. So L equals to 128, so you can represent it as 2 power 7. So N ante number of bits present per sample will be 7 there. And for L256, can you tell me how many number of bits per sample are there?
8 bits, ma'am. 2 power 8.
Yes, 2 power 8 is 256. So we can represent it as, so it as 8 number of bits per sample. So we need to calculate the SNR in dB for L128 and L256 PCM system. And always remember that if we have some extension problem like this, don't approximate the SNR dB expression. So meeku as usual ga ela aithe untundo ave expression. Okay, even the decimal points also, please keep it like that. Don't approximate 7.78 to 7.8 because we have some extension problem is there. So if we do like that, the answer may differ. Okay, so that's why don't directly approximate the final expression of SNR in decibels. Keep it as usual and evaluate the extension problem. So what is the extension problem? Let us see it in the next slide. So we need to calculate the SNR in dB for L128 and L256 PCM. When L equals to 128, so here you can represent it in the form of 2 power 7. So N number of bits per sample will be 7. So you can call number of bits per sample as number of bits per frame. Okay. So what is the expression? 7.78 plus 6.02 N. Please substitute N value as 7 so that you can get the SNR in dB for 128 PCM system. So you will get it as 49.92 decibels. Okay. Similarly, for L256, number of bits per sample N will be 8. So 7.78 plus 6.02 multiplied by 8. So you will get it as 55.94 decibels. Okay. So within this module, we can conclude that each and every student should be able to evaluate the quantization error. Similarly, quantization noise power, and signal to noise ratio for a PCM system under uniform quantization, because this whole evaluation we performed by considering the step size as uniform. So we consider step size as delta and we calculated the SNR. So till with this, almost all the noise portion of SNR has completed. Noise portion for PCM system has completed. So we need to compare it with delta modulation, which we can study in the further modules. Okay. Now what is the conclusion from this module? So I will call one student. That student should be able to tell me the expression for quantization error, quantization noise power and signal to noise ratio under uniform quantization. K9 is there?
Yes, ma'am.
Okay. So please tell me the expression for quantization noise power. Quantization noise power for PCM system.
Delta square by 12.
Delta square by 12. What is delta?
Step.
Step size ఎలా represent చేస్తారమ్మా? Step size delta equals to, tell me the expression for that.
2x max by 2 power n.
Yes, 2x maximum by 2 power n. You only tell me the expression for SNR for PCM system. Tell me the general expression and then you can tell it in decibels.
Vp into L square by
Yes, 3p L square by
S square max.
x square max, where p is the assumed signal power. Now please tell me it in decibels. If the input signal x of t is normalized, then p value will be less than or equal to 1. Then what is the value of SNR in decibels for that type of PCM system?
SNR less than or equal to 4.8 plus 6 in dB.
6 in dB. Okay. Now you only tell me one more question. If the amplitude of message signal is given as capital AM, then what will be the signal power? చెప్పండి. If the message signal m of t is given as am cos 2 pi fmt, what is the signal power? Signal power p ఏంటి అవుతుందమ్మా?
Less than or equal to 1. P less than or equal to.
అది జనరల్ గా, బట్ నేను ఐఎమ్ గివింగ్ యూ సిగ్నల్ x of t as am cos 2 pi fmt. If the signal x of t is given as am cos 2 pi fmt, what will be the signal power? అంటే ఇన్ జనరల్ గా అయితే నార్మలైజ్ చేస్తే p less than or equal to 1 ఉంటుంది అని చెప్తున్నారు. బట్ if the signal x of t is am cos 2 pi fmt, what will be the signal power p?
AM square by
am square by 2r. If the for normalized resistance r will be 1 ohm, so that's why am square by 2. Okay, so like this we need to appudu enti avutundi SNR 3 am square into L square divided by 2. Okay, SNR will be 3 am square L square divided by 2 for this type of x of t. So in general you will get this type of problems in the examination, where signal power will be directly am square by 2r, and upon substitute r as 1 ohm and x max as 1 volt, you will get SNR as 3 am square L square by 2. Okay, so this type of problems you will get in the examination. Okay, thank you very much, ma. K9, thank you. So till with this we completed the module 4, and in the next class we can continue with the module 5, where you can see the drawbacks of this uniform quantization. In the uniform quantization, we cannot provide like constant SNR. Okay, so we can see that in the next class, and the importance of non-uniform quantization for PCM system. Okay, with this I will wind up the session. Okay, so this is the learning outcome for this module. So wait for 2 minutes, I will take the attendance. So any doubts?